Hello everyone, this is Victor, and I'll be speaking about RobotCore, an open architecture for hardware acceleration in ROS2. Let me dive into it. This work is mostly funded by Acceleration Robotics, a firm focused on designing customized brains for robots to hasten their response time. It does so by creating custom compute architectures for high-performing robots through hardware acceleration solutions while remaining accelerator-agnostic and also robot agnostic. And this happens through FPGAs and GPUs in combination with CPUs. This work is done in collaboration with Harvard University, Klagenfurt University, and others. I'd like to give all the credit to my co-authors Sabrina, Brian, and BJ, who contributed heavily to this work. Moving faster or with more dexterity requires faster perception computations. Atlas in the slide uses perception to identify, navigate, and jump around obstacles. Edge perception is key to navigate under environments that change, which are most in the human world. Atlas leverages a time-of-flight depth camera to generate point clouds of the environment at 15 Hz. The point cloud, is a large and dense collection of range measurements which needs to be processed at the edge directly in the robot for smooth behaviors, reducing any latency from the sensors and all the way into the actuators. By leveraging hardware acceleration, Atlas's perception extracts surfaces from this point cloud, which are then used to plan actions in the order of tens of milliseconds, all happening on the edge. This is precisely what we present, the capabilities we present with RobotCore framework, an open architecture for hardware acceleration in ROS2. In a nutshell, RobotCore framework are a series of extensions to ROS2 that allow to easily leverage hardware acceleration in a ROS-centric manner and build custom computer architectures for robots, or robot cores, as we call them, and that's where the name comes from. Simply put, RobotCore provides a development, build, and deployment experience for creating robot hardware and hardware accelerators, similar to the standard non-accelerated ROS development flow. In the figure, you have in here a series of depictions of how we can transform a CPU-centric computational graph built with ROS2 into variants that leverage FPGAs, GPUs, or even combinations of everything. After developing our corresponding architectural improvements, we do have a layer of an integrated tracing and benchmarking methodology that does allow us to actually measure and quantitatively iterate over improvements of our robotic architectures. Now, we've explained how a RobotCore framework allows you and gives you the tools to build up these architectures to improve computational graphs with hardware acceleration. But what are these essentially underlying computational resources that we can leverage? Well, let me quickly go through each one of them and give you a sneak peek through a metaphor. And we're going to be using an industrial metaphor. CPUs can be understood as traditional workshops wherein essentially you can produce pretty much anything. However, the process of production of this output is serial. Happens one task at a time. Modern CPUs have various cores, various of these workshops, and thereby can do various of these output objectives in parallel. However, each one of these workshops is running somewhat independently and also through serial tasks or operations at each clock cycle at a time. Now, GPUs can be understood roughly as an industrialized version of this workshop. We have, instead of one worker, many workers working in parallel and doing exactly the same operation. We have experts designing these master plans or acceleration kernels for GPUs. And they certainly come together as many packed within a GPU. We don't have just one industrial workshop, but many more. Skipping over ASICs for the sake of time, let me give you a sneak peek into FPGAs. So FPGAs essentially represent adaptable factories. Factory that can produce one day boxes and the next day cylinders. It is flexible and adaptable. It can be reconfigured. There's an expert architect that can do so via software. However, it's highly complex. And though this complexity is significant, it does come with the fantastic trade-off that the output is generally low power. It does provide one of the highest performances, and also it is highly deterministic because it is built in hardware at the end of the day. That's precisely what we are leveraging within RobotCore, the possibility to combine all these different resources. And we haven't done so just for one particular technology, but for a bunch of them, leveraging CPUs plus FPGAs or CPUs plus GPUs and combinations across multiple vendors, and by building on top of production-grade operating systems built with Yocto. Another major contribution we've made with RobotCore is the proposal of a low overhead tracing and benchmarking framework capable to provide benchmarks with real-time characteristics in mind. We are building on top of the Linux Tracing Toolkit next generation, LTTng, and you've got in here more details of our non-functional gray box approach to benchmarking. The last contribution, which is relevant, is that though we can obtain acceleration factors by leveraging particular accelerators such as the FPGA in here, the downside of this is that often we need to change the architecture. So we have designed an intra-FPGA ROS2 queue, which allows us essentially to maintain computational graphs as they are and leverage AXI4 stream interfaces to create this intra-FPGA ROS2 communication queues with data passing across ROS2 nodes and the FPGA in a essentially in an abstracted away manner. Altogether, all of our contributions are being grouped as part of standardization efforts within the ROS2 community. And the last bit we wanted to share is that we are super excited to bring RobotCore to the next stage, to the next phase. We are launching a physical device, also as part of the community contributions, called the Robotic Processing Unit, which is specialized in ROS2 computations. If you'd like to learn more, come and join us and talk to us directly. Thank you.